Welcome back, students. In this video segment, we will cover one section, section 3.5, double angle and half angle formulas. In this video segment, we're going to finish up the second half of the handout that I have posted on Canvas entitled Identities or Trig Identities. In section 3.4, we talked about sum and difference formulas, the top 6 formulas on the second page of the identity sheet. In this segment, we finish up the sheet. We look at the remainder of the formula. So let's get started. First of all, it looks like a really daunting task to finish up that second side of the handout. It's really not. A lot of the formulas are repeats. They're just different forms of the same identity. And another thing is that if you forget some of these identities, and you're likely to, we're human, we forget things, you can retrieve them specifically on an exam or something in Calculus 2, where you're going to be seeing this stuff really, really heavily. You can use sum and difference formulas to retrieve a lot of the information on this page. So let's get started with this section. Section 3.5 starts with, we're going to start with a true or false question. True or false? True or false? And the question is, the statement is, the sine of 2 theta equals 2 times the sine of theta. And I'll give you a hint. A lot of Calculus 1 students get this wrong. A lot of Calculus 1 students get this wrong, at least in the last 3 decades that I've been teaching first semester calculus. A whole lot of students get this wrong, have gotten this wrong, a large percentage. So you can pretty much guess that it looks good. It looks like we should be able to factor that 2 out, but it's too good to be true. It doesn't work. It simply doesn't work. You can't factor constants out of trig functions like this. In fact, you can't factor constants out of almost any function that you're going to deal with as a STEM major. So it's false. However, we do have an identity that's close. We have an identity called a double angle formula. A double angle formula. Formula, which is used very early in physics, very, very early in physics. And specifically, you're going to use this formula in physics when you study projectile motion. And the formula goes like this. It says that the sine of 2 theta, it starts out the way we would like to have it happen. It starts out with that 2 appearing to be factored out, but we end up needing to multiply by cosine of theta. And this formula, like all the formulas from our identities from both sides of this handout, you ought to memorize. You're going to see these formulas again over and over again in both calculus and physics and engineering math and a whole host of other areas in STEM field math or STEM field courses. Okay, so I mentioned that you're likely to forget things. We all are. We're human. And on a Calculus 2 exam, your instructor is not likely to give you an identity during a test. So we have to be able to either memorize or retrieve these identities if our memory fails us. So here's how we can get this. Here's how we can get this formula. So the sine of 2 theta is the same thing as the sine of theta plus theta. And we just finished a section where we dealt with the sine of alpha plus beta. And that looks like the sine of alpha times the cosine of beta plus the cosine of alpha times the sine of beta. Okay, if this doesn't look familiar to you, then you're looking at the wrong video. You should be back in section 3.4. It's mostly a joke. You're probably not watching this video unless you've already done section 3.4. Yeah, you can't do 3.5 without 3.4. So I'm going to substitute into the red sine formula, alpha and beta both equal to theta. So this is sine of theta, cosine of theta plus cosine of theta times sine of theta. Well, multiplication is not sensitive to order. So this is sine theta cosine theta plus another sine theta cosine theta. And that gives us 2 sine theta cosine theta. Very simple algebra there. And this formula, like I said, is going to appear very, very, very early in physics. It's involved in determining specifically the angle that a projectile should be fired, let's say above the horizon, in order to achieve maximum range. Okay, so if that's theta, you actually use the double angle formula to obtain that angle that will give you the farthest range of a projectile. Okay, and of course, when it neglects, it's a very early example, so it neglects wind resistance and stuff like that. So okay, so back to math. So we have one double angle formula for sine. Sine of 2 theta equals 2 times the sine of theta times the cosine of theta. We have 3 double angle formulas for the cosine of 2 theta, and they should all be memorized. There, if you don't have your identity sheet opened up or copied, you should access it on Canvas if you can, and maybe have a copy in front of you, because we're going to be referring to it. There are 3 double angle formulas for the cosine. Cosine, oops, I wrote cosine of 3 theta. I was thinking 3 formulas, and these are double angle formulas. So cosine of 2 theta equals cosine squared theta minus sine squared theta. That's one of the formulas, which looks a little tricky. It looks like it doesn't make sense at first for a lot of students, because we know that cosine squared theta plus sine squared theta always equals 1. So if you simply by changing the middle sign in cosine squared theta plus sine squared theta equals 1 to a minus, we don't get 1 anymore. We get cosine of 2 theta. That's actually true. Okay, cosine of 2 theta also equals 2 cosine squared theta minus 1, and 1 minus 2 sine squared theta. You should memorize all of these formulas, but like I said, you can retrieve them if you forget them. Suppose you forgot all 3. Simply take cosine of 2 theta equals the cosine of theta plus theta, and then refer to a formula for the cosine of alpha plus beta from our last section. It's cosine alpha times cosine beta minus sine alpha, sine alpha sine beta. Okay, and then replace alpha and beta with theta. And we get our result almost immediately. We get cosine theta times cosine theta minus sine theta times sine theta. And of course, that's cosine squared theta minus sine squared theta. Okay, boom, we got it. Okay, so what if we remember this one and don't remember the second one, 2 cosine squared theta minus 1? Well, we know that sine squared equals 1 minus cosine squared, because sine squared plus cosine squared equals 1. Well, if you distribute, get rid of the parentheses, so distribute a negative 1, you get cosine squared theta minus 1 plus another cosine squared theta. And that's 2 cosine squared theta minus 1. So there's, if you forgot everything, oops, let me get rid of that. Not everything, but if you forgot all of the double angle formulas, you can retrieve it. Retrieve it by using a sum and difference formula, sum formula. And from that, you could obtain the second one. What if you forgot the third one and you remember the second one? This is the really nice thing, if I can have your permission to say nice, associate the word nice with identities. The really nice thing about identities is they can be used to retrieve other identities. So cosine squared theta is 1 minus sine squared. I'm just substituting into the last expression for 2 cosine squared theta minus 1. Distribute the 2. Subtract 2. 2 minus 1, 1 minus 2 sine squared theta, and there is the third formula. Okay, so this is a fixable problem on a test if you forget identities, but you have to remember something. What did we have to do to get all these three identities? You had to remember a formula or formulas for the cosine of alpha plus beta. That's why we study them first. Those formulas above for sine and cosine and tangents for the sums and differences can be used to retrieve every single identity below. So yeah, they're really very important. Let's do a numerical problem. So for example, find the exact value. Find the exact value. So what does that mean for us? It means no calculator. Find the exact value of the cosine of 2 theta and something we don't have yet a formula written for, tangent of 2 theta, if, let's say, the cosine of 1 theta is negative 2/3, the cosine of theta is negative 2/3, and theta is between pi over 2 and pi, so that puts theta in quadrant 2. Okay, there's a mistake that's made often. So this is a common mistake. I'm going to identify as such here. Common mistake. I'm going to see if I can spell mistake. Or write it a little better. Okay. Mistake. All right, I'll take it. A common mistake is to take the cosine of theta equals negative 2/3, and that's correct. That's given. Multiply by 2 on both sides. Now that's not a mistake. You can do that. And multiply 2 times negative 2/3 to get negative 4/3, and then bring the 2 inside. That's the big problem. No, you can't do that. To get cosine of 2 theta equals negative 4/3. It happens. It happens. And it happens often enough that I'm taking valuable video time to show you this mistake. Don't do it. You can't factor numbers outside of trig functions, or you can't bring them in as factors. You cannot do it. You cannot do it. That 2 and 2 cosine of theta is stuck there. You cannot bring it in, and you can't factor a 2 out of the angle if it were cosine 2 theta. So, okay. There is by the way, there is a clue in this false result that tells us that it's impossible. What's wrong with the statement cosine of 2 theta equals negative 4/3? What's wrong with that statement? What's wrong with the cosine of 2 theta equals negative 4/3? It's a blaring thing to us. It's shouting at us almost that that's impossible. What's the minimum value of the cosine of any angle? It's negative 1. And negative 4/3 is less than negative 1. So this is absolutely impossible. You can't take the cosine of a real angle and get something less than negative 1. It just won't happen. So it's pretty obvious that this is a mistake. So let's do this the correct way. So back to our given information. Our given information was that the cosine of theta equals negative 2/3. And theta's in quadrant 2. I'm just moving it down here. Okay, so we can actually begin the problem. Here we go. Okay, so let's do it. Get rid of all more. Okay. Well, I want the cosine of 2 theta. The cosine of 2 theta. The cosine of 2 theta, I have 3 formulas for. I have cosine squared theta minus sine squared theta. I have 2 cosine squared theta minus 1. I'm just reviewing them with you. And I have 1 minus 2 sine squared theta. Which one should we use? Which one should we use? A, B, or C? Which one would be the best choice? There is a best choice. They can all be used. But which one is the best choice for us? I'm trying to make my B look more like a B. Okay. It is not A or C. That's your hint. A or C will work. We could use A and C, but you want to avoid it. Why? What are we given? We're given some information about the cosine of theta. So why not use an identity that involves cosine of theta? In fact, that's a really powerful rule of thumb. Try to use a formula that involves the stuff that's given. If you can't always do that. If you chose, for example, to use formula C that I've identified with a red C, you first have to find the sine of theta. And there are a couple of problems with that. One, you may make a mistake in doing that. So every time you write something, you've introduced the chances that you're going to make a mistake. So if you want to use a formula that involves sine, first you got to find the sine. If you screw that up, your cosine of 2 theta is going to be wrong. The next thing is, and this is sort of a subtle thing for us right now, is if we have to find sine, ultimately we may want a decimal approximation, in which case we'd have to round off. So if I wanted to go through using the red identity C, I would need to find sine. I may round it off using a calculator, in which case I'm introducing error, and then use that quantity with error built into it to estimate cosine of 2 theta. And every time you use something with error in it to compute something else, the error compounds. It gets worse. Okay. The big one for us for right now is you want to try to avoid using formulas. Rather, let me say it this way. You want to try to find a formula that uses stuff that we're given. Okay, the less you have to find, the less your chances are for making mistakes. Okay, in any case, let's use the formula cosine of 2 theta equals 2 cosine squared theta minus 1. That's the best choice. That's the best choice. So I'm going to substitute for cosine of theta, negative 2/3. So 2 times negative 2/3 squared, because it's cosine squared, minus 1. 2/3 squared is 4/9. Minus 1. 2 times 4/9 is 8/9. Because it's like having 2 over 1 times 4 over 9, 8/9. And 8 over 9 minus 9 over 9 is negative 1 over 9. So the cosine of 2 theta is negative 1 over 9. Okay. Now, suppose I want to find the tangent of 2 theta. That was our next part of this two-part problem. I want the tangent of 2 theta. I need a formula for tangent of 2 theta. And I have one. It's the next double angle formula on our list. There's a really neat way to memorize it. The tangent of 2 theta starts out like the sine of 2 theta does. It starts out with a mistake. 2 tangent theta. Remember how sine of 2 theta started out with a mistake, 2 sine theta, and then you fix it by multiplying by cosine. Well, tangent does the same thing. For the formula for tangent of 2 theta works the same way. Tangent of 2 theta, you can sort of make a mistake and factor out the 2. It never works. Never works to have that without some sort of adjustment. And then divide by 1 minus tangent squared theta. And that's the formula for the tangent of 2 theta. Okay, a really nifty formula. Okay, so something to note here is the denominator 1 minus tangent squared. It may have occurred to you that it looks like it should simplify. It doesn't. It doesn't. We know that 1 plus tangent squared is secant squared of theta, but 1 minus tangent squared is about as simple as we can get. Okay, so back to our problem. We are given the cosine of theta equals negative 2/3, and theta was between pi over 2 and pi. Theta's in quadrant 2. And I want the tangent of 2 theta. Well, the formula says I need the tangent of theta to do this. So I'm going to have to find something. I'm going to have to use the information that I know, namely cosine is negative 2/3, and find tangent of 2 theta, or tangent of 1 theta. This is an old problem for us. We've done this bunches of times before. So here's the angle theta, quadrant 2. Here's the angle theta. So the tangent of the tangent of theta, we can find. We have formulas for doing that. If you want to sort of a kind of a review of section 2.4, the cosine is negative 2/3. So we could use a Pythagorean theorem to find the remaining side of that virtual triangle, or the y-coordinate of that point in quadrant 2. So negative 2 squared plus b squared equals 3 squared. This is old news for us. This is 4 plus b squared equals 9. B squared equals 5. So b equals plus or minus radical 5. It's in quadrant 2, so radical 5. Radical 5. Okay, so I want you to see that b. I can turn it into radical 5. That was kind of cool. Okay, so the tangent of 2 theta equals, a stray mark makes it look like tangent of minus theta. I'll have to get rid of that straight mark. Okay, tangent of 2 theta equals 2 tangent theta over 1 minus tangent squared theta. Okay, so let's put in the information. We know tangent of theta from our diagram here is negative radical 5 over 2. Just picking it right off the figure, over 1 minus tangent, negative radical 5 over 2. Remember, tangent is opposite over adjacent, radical 5 over negative 2. And then we use some algebra to fix this, or to finish this off. So 2 times negative radical 5 over 2 is negative radical 5 over 1 minus radical 5 over 2 squared. Well, radical 5 squared is 5, 2 squared is 4. So this is nothing more than negative radical 5 and 1. See that 1 down there in that denominator? I'm going to write it as 4 over 4. 4 over 4. And 4 over 4 minus 5 over 4 is negative 1 over 4. Okay, and when the negative cancels, negative over negative is positive, invert and multiply. 4 radical 5. 4 radical 5 is the value of the tangent of 2 theta. Okay, this isn't real exciting stuff, but let me assure you that if you're a science major, and you most likely are, most people who take trig are headed toward calculus, and most people who take calculus are headed for a STEM major like physics or engineering or stuff. So if you're a science major, you're going to be using these formulas to do a lot of interesting things in your chosen major or field. Okay, trig is everywhere in the sciences. So here's a popular example. If you're going to take calculus 2, and almost 100% of you guys are headed toward that, if you're going to take calc 2, then you're going to do this problem again, but in a very, very different setting. I can almost guarantee you that. If you take me for calc 2, I absolutely guarantee it. So here's the problem. It's going to look a little strange at first. Reduce to first powers of trig functions. Trig functions. And here's our problem. The problem is sine fourth theta. In calculus 2, a lot of these formulas on this page of the identity sheet are going to be used. In particular, there's an operation that there's a process that you're going to do in calculus called integration that is not real friendly to powers of trig functions higher than 1. There's a process you're going to do in calculus called integration that doesn't deal real well with the fourth power of sine, or any power of a trig function other than the first power. Calculus is very friendly. The process is very friendly to the first power of trig functions. So that's the reason why we want to reduce this somehow to the first power. To do this, we have power reducing formulas. It's our next formulas on the list. Power reducing formulas. Okay, let's talk about two of them. Sine squared theta is in fact the same thing as 1 minus the cosine of 2 theta over 2. Now just concentrate on that formula and the name of that formula for right now. Concentrate on the name of that formula. It's called a power reducing formula. Why should it be called that? Well, look on the left hand side. It has sine squared. Look on the right hand side. It has cosine of 2 theta. On the left hand side, you have the second power of a trig function. On the right hand side, you have the first power, cosine of 2 theta. The angle's 2 theta on the right, but that's not a power. That's the cosine of the angle 2 theta. It's the first power of cosine. Similarly, the cosine squared of theta equals 1 plus the cosine of 2 theta. So you're starting to notice that the number of formulas are starting to get overwhelming. So I want to reassure you, there's nothing new here. Nothing. Now, what do I mean by there's nothing new here? I give you two formulas that are new, and then I'm saying there's nothing new. What does he mean? Well, the cosine of 2 theta, one of the formulas for the cosine of 2 theta said cosine of 2 theta equals 1 minus 2 sine squared theta. Okay, that was one of the three formulas for the cosine of 2 theta. Now, solve this equation that I have in red for sine squared. So add sine squared to both sides. So 2 sine squared to both sides, make it positive. Subtract cosine of 2 theta from both sides. Then divide both sides by 2. This is just a restatement of the double angle formula for cosine, solving for sine squared. Similarly, for cosine squared, you solve another formula for cosine of 2 theta, another one of the three formulas for cosine squared. Okay, so this is completely retrievable from the double angle formulas for cosine. Now think about this. Suppose you forgot all of the double angle and power reducing formulas. So you use a sum formula, cosine of alpha plus beta, to get the formulas for cosine of 2 theta, and then you solve for say sine squared to get this power reducing formula. So there's not a lot of new stuff on the page below the first six sum and difference formulas. Okay, and they're very easily retrievable if you forget them. Okay, so let's do this. I want to take sine to the 4th theta and reduce it to first powers. Well, I don't have a formula for sine 4th, but I certainly have one for sine squared. And little algebra, very little algebra, says sine 4th equals sine squared times sine squared. X to the 4th equals x squared times x squared. That's all I'm using here. That's all I'm using in this first line right there. Trying to draw an arrow, and it's getting uglier and uglier here. Okay. All right. So at this point, I'm gonna substitute sine squared as 1 minus cosine of 2 theta over 2 times the same thing, 1 minus cosine of 2 theta over 2. And I'm going to multiply this out. Well, the 2's in the denominators can multiply out. We can gather those together. Then we're stuck with multiplying 1 minus cosine of 2 theta times 1 minus cosine of 2 theta. So we're going to use a standard, the FOIL method we learned in Algebra 1. First 2, 1. Outside 2, minus cosine 2 theta. Inside 2, minus cosine 2 theta. Last 2, minus times minus, negative times negative, plus cosine squared 2 theta. Okay, so this is 1/4. 1 minus cosine 2 theta minus another cosine 2 theta. That means I have two of them. So minus 2 cosine 2 theta plus cosine squared 2 theta. Well, we're not out of the woods yet. We're not out of the woods yet. The reason why we're not out of the woods yet is right there. That power is 2. I need 1. Need first power. And that's 2. That's not good. That's not good. So I'm going to get rid of that power. I'm going to not just erase it. I'm going to get rid of it legitimately. I'm going to use a power reducing formula for cosine. Okay, so the power reducing formula for cosine, put way down here in the lower left. Cosine squared is, it's above, and I want us to have it available for us. Cosine squared theta is 1 plus cosine of 2 theta over 2. Okay, so, but I don't have cosine squared theta. I have cosine squared of 2 theta. Okay, so in this power reducing formula for theta, I'm going to need to replace theta with 2 theta. So I'm going to take that theta out, and in green I'm going to put 2 theta. So I'm going to go to the right hand side, and I'm going to take that theta out, and in green I'm going to put 2 theta. Okay, so let's go back up to our identity. Let's see, let's go back up to our identity then. So this equals 1/4 1 minus 2 cosine 2 theta plus cosine squared 2 theta is 1 plus cosine of 4 theta over 2. If I replace in the power reducing formula for cosine squared theta, if I replace theta with 2 theta on the left, I got to replace theta with 2 theta on the right. It gives me a total of, on the right, 2 times 2 theta is 4 theta. Okay, so let's take this further. So this equals 1/4 times 1 minus 2 cosine of 2 theta. And I can split this up into 2 fractions, 1/2 plus 1/2 cosine of 4 theta. Okay, all I did is I used that let's say 1 plus a over 2 is the same thing as 1 over 2 plus a over 2. Just another little algebra formula. Okay, we're almost there. We're almost there. Let's clean this up. Combine like terms. We have 1 and we have plus 1/2. 1 plus 1/2 is 1.5, or 3/2. Minus 2 cosine of 2 theta plus 1/2 cosine 4 theta. And maybe distribute the 1/4 so we get 3/8. Minus 2/4, which is 1/2 cosine of 2 theta, plus 1/8 cosine of 4 theta. Okay, let's see, I'm going to make sure I believe all this. Let's see, looks pretty good. Okay, so let's get through the rest of this page. And it still looks like, oh my God, there's more than 1/4 of a page left, and I want to finish it up. It won't take long. The next series of formulas are entitled half-angle formulas, and we'll look at. Actually, we only need to look at the first 3 of them. Let me explain. One of them says sine squared alpha over 2. These are half-angle formulas. Half-angle formulas. So out of the blue, it looks like we have a brand new formula. Sine squared alpha over 2 is 1 minus cosine alpha over 2. It is absolutely not new. We've seen it. We saw it just 5 minutes ago, max. But we saw it in a different form. We saw sine squared theta equals 1 minus cosine of 2 theta over 2. It's the same formula. Replace theta with alpha over 2 on both sides of the equation. Replace theta with alpha over 2 here, and replace theta with alpha over 2 on the other side. If you replace theta with alpha over 2, you get sine squared of alpha over 2 on the left-hand side. On the right-hand side, you get 1 minus cosine of 2 times alpha over 2, which is just alpha, all over 2. So it's not new. And if you'll notice on the identity sheet, directly to the right of it, I have another formula. It's the same formula. if you take the square root of both sides, you have sine of alpha over 2 equals plus or minus the square root of 1 minus cosine of alpha over 2. So it's an equivalent, absolutely equivalent formula. There's nothing new in that formula. So it looks like there's a lot of information on that page, and there is, but it's information that's repeated. It's information that's repeated over and over again, just in a slightly different form. Okay, so let's finish this video segment by looking at two important formulas. Both of them have a common mistake, so I'm going to try to bring those up as we go along. So here's our next to the last problem. Use an appropriate half-angle formula to find the exact value of, let's say, the cosine of 15 degrees. Okay, we've done something like this before, but the common mistake is to use the method that we did before to do it. If you missed it, if you missed the problem, we've done this before. Before, we wrote the cosine of 15 degrees equals the cosine of 45 minus 30 degrees, and then we used an appropriate, not half-angle formula. This problem calls for a half-angle formula. We used a sum or difference formula. Cosine 45, cosine 30, plus sine 45 degrees, sine of 30 degrees. And of course, these numbers are old friends. We know them, or we should know them by now. This is radical 2 over 2 times radical 3 over 2 plus radical 2 over 2 times 1/2, and then combine radicals. Radical 2 times radical 3 is radical 6. Oops. Add a little extra radical 6 there. It's radical 2. Radical 6 plus radical 2 over 4. Now, this would be an absolute mistake on an exam. I want you to hear that again. This would be absolutely wrong on an exam. If the directions were to use an appropriate half-angle formula, you would get absolutely no credit for this. So if it was an 8-point problem, minus 8. Before you get too angry, the reason is you didn't follow directions. You must absolutely follow directions on exams. Now, this is what an exact value of the cosine of 15, but it is not obtained correctly, and it looks very different from the form that we're going to see. So now we're supposed to use an appropriate half-angle formula. The half-angle formula that we're going to use, of course, is 1 for cosine. It's going to look like cosine of alpha over 2 equals plus or minus the square root of 1 plus cosine of alpha over 2. Where did I get that? It's right on our identity sheet. So don't worry if it looks unfamiliar to you. This is the first time you've seen it. It's okay. It's right up there. It's derived very similarly to the half-angle formula that I just derived for you for sine squared alpha over 2, or sine of alpha over 2. Okay? All right. So let's do this. So the first mistake is that the tendency to use the wrong formula to get this answer. The second mistake is coming up. So how do we find the cosine of 15 degrees? Well, the cosine of 15 degrees, using a half-angle formula, is the cosine of half of how much? It's half of 30 degrees. Okay, 15 is half of 30, is 30 divided by 2. So this equals plus or minus the square root of, and in the identity I'm going to substitute what for alpha? What am I going to substitute for alpha? 1 plus cosine of how much? Alpha is 30. Okay, Don't forget the plus or minus. That's the second mistake, is to not put a plus or minus there, or to choose the wrong sign. So this is plus or minus square root of, and the cosine of 30 is radical 3 over 2. Okay, I'm going to do a little algebra on this for a little manipulation that we learned in algebra for the radicals. We're going to multiply by 2 over 2. Simplify things a little bit. So this is, if I distribute the 2 into the numerator, 2 plus radical 3 over 4. And in the denominator, square root of 4 is 2. So this is plus or minus 2 plus radical 3 over 2. Now, 15 degrees is in quadrant 1. And in quadrant 1, all the trig functions are positive. So this is radical 2 plus another radical under the radical sign over 2. And that's a very different answer than radical 6 plus radical 4, radical 6 plus radical 2 over 4. This is how we would get an answer using an appropriate sum and difference formula. This is a very different looking answer using a formula for half angles, half angle formulas. So above would be an incorrect answer. Answer for our problem, because it's not using a half angle formula. Okay, this is something that will be very dangerous for you on your next exam. You must read directions, and you must read them very, very, very carefully. Okay, which you really ought to get used to in the STEM fields, in science, technology, engineering, and mathematics. The devil's in the details. You absolutely must read directions very, very, very carefully in the sciences, or follow directions very, very carefully. Okay, so here's our final example. And it contains a common mistake too. So we're given here the cosine of theta equals 3/5, and theta is between 3 pi over 2 and 2 pi. And I want to find the sine of theta over 2 and the cosine of theta over 2. Okay, seems like a perfectly innocent little problem. There's an extremely common mistake with it though that I'm gonna identify when we get to it. Okay. Well, we're gonna need a diagram of our angle. So I'm gonna draw that for us here. We're gonna need our angle pictured here. Okay, so here's our angle. Our angle's in quadrant 4. How do I know it's in quadrant 4? Because the problem says it's in quadrant 4. So it's between, theta is between 3 pi over 2 and 2 pi. And the cosine is 3/5. Here's our angle theta. That's theta, and the cosine is 3/5. 3. Oh, wait a minute, that's impossible. Cosine of theta, oh no, that's okay. 3/5. Fooled myself there for a second. Let me move that theta out of the way. I thought, no, it has to be negative here, 3/5. The sign is negative. Pythagorean theorem gives us -4 for the y coordinate of the point corresponding to the angle in standard position, theta. Okay. So let's do this. I'm going to start way on the left here, and I can do both of them, both sine and cosine in one line each. So I want the sine of theta over 2 and the cosine of theta over 2. sine of half the angle and the cosine of half the angle. Make my parentheses better. All right, so the formula for the sine says it's plus or minus the square root of, they both have plus or minus the square root of, plus or minus the square root of. The formula for the sine of theta says that theta over 2 says it's plus or minus a square root of 1 minus the cosine of theta over 2 and 1 plus the cosine of theta over 2. So they look very similar. So this equals plus or minus. I'm going to leave the plus or minus until the very end. And that, by the way, it's the plus or minus that causes the big mistakes. Okay, I just want to get a little more room this way. Okay. So let's do this. So this is plus or minus 1 minus the cosine of theta was 3/5 over 2. And for the sine, it's almost the same. 1 plus 3/5 over 2. I'll let you know when we get to the really common mistakes. So this is plus or minus. 1 minus 3/5, that's like 5 over 5 minus 3 over 5 is 2 over 5 over 2. Plus or minus 5 over 5 plus 3 over 5 is 8 over 5 over 2. Radical extends. So almost everybody gets it right so far. The mistake is the very end here. If I invert and multiply, and it's underneath the first radical, 2 over 5, and then multiply by 1 over 2, I get the square root of 1/5. Or plus or minus 1 over the square root of 5. We can leave it unrationalized, or denominator not rationalized. So this is plus or minus, if I invert the 2 over 1, invert and multiply, I get 8 over 5 times 1 over 2 is 4 over 5. And this isn't, the mistake hasn't been made yet, the common mistake. And here's where the mistake happens, and it's a big one. If each of these is like 4 points or 8 points on a test, the mistake usually costs the student everything. And it's not at the point. The mistake is in the plus or minus. The mistake is in the plus or minus. So where's theta? Where is theta? Theta's in quadrant 4. Theta's in quadrant 4. Theta's in 4. Here's the mistake. We're looking for sine and cosine of theta over 2. Well, in quadrant 4, the sine of theta is negative, and the cosine of theta is positive. So the mistake is for students to say that the sine of theta over 2 must be, well, negative, and the cosine of theta over 2 must be positive. Wrong. And it's tragically wrong. Wrong, wrong, wrong. We're not finding the sine and cosine of theta. We're finding the sine and cosine of half of theta. If theta is in quadrant, and listen carefully to this. This could be very expensive on an exam. If theta is in quadrant 4, where is theta over 2? Where is theta over 2? Well, some are going to be able to see that easily. Some are not so much. If theta is in quadrant 4, and it is, where is theta over 2? It must be in quadrant 2. Why is that? I'll show you 2 ways to see that. This is very important. Theta is in quadrant 4. So one way to do this algebraically, to show you that half of theta is in quadrant 2, is to state the algebraic statement that says theta is in quadrant 4. That means theta is between 3 pi over 2 and 2 pi. Now multiply all 3 sides of this inequality by 1/2. So if theta is in quadrant 4, theta over 2 is between 3 pi over 4 and pi. Where is theta if it's between 3 pi over 4 and pi? That puts us right here. It puts us in quadrant 2. quadrant 2, exclamation point 3 times. Okay. Now that's the algebraic way of saying that. Geometrically, it's pretty easy to see too. Picture an angle in quadrant 4. Theta. Theta's in quadrant 4. Now imagine snipping half of that angle off. Remove half of that angle. Remove half of the angle. Remove half the angle. I'm just physically just removing half the angle. That leaves this amount for theta over 2. I would do the algebra thing. I would do this algebraically. In any case, half of theta is in quadrant 2. Theta over 2 is in quadrant 2. And in quadrant 2, the sign is positive. Remember, I'm just using all students take calculus. In quadrant 2, the sign is positive. So that would give us 1 over radical 5. Or radical 5 over 5 if you rationalize the denominator. And the cosine's negative. We would get the absolute opposite answers that you get by making a mistake. When you're finding sines and cosines of theta over 2, you have to cut the angle in half. I recommend figuring this out algebraically. It won't ever fail you. I recommend you do it this way, which I'm now identifying in green. So let me, to finish the segment, if theta, just a quick one, if theta is in quadrant, let's say, 3, where is theta over 2? Okay, let's do this algebraically. If theta is in quadrant 3, that puts theta, let's say, like this. Here's theta in quadrant 3. Where's theta over 2? It seems like it should be in quadrant 2, but we can do this very easily. Theta in 3 means that theta is between where and where? It's between pi and 3 pi over 2. So multiply all three sides by 1/2. And theta over 2 must be between pi over 2 and 3 pi over 4. That's quadrant 2. Okay, so you can always figure out where theta over 2 is by using a little bit of algebra. This is extremely common as a mistake, and it's often very, very costly on an exam. Very, very, very expensive on an exam, just making a mistake on a sign. So that's the end of this section. Go ahead and get started on homework as soon as you can for section 3.5, and I'm looking forward to talking with you all again very, very soon.